In my earlier video, I had seen what is the annihilating polynomial, what is characteristic polynomial, and what is the minimal polynomial. And today's first goal of the lecture is eigenvalue of characteristic polynomial always same as eigenvalue of minimal polynomial. This is our first goal of this lecture. I will prove it. Next, I will see different type of example which had come in competitive exam. So at first, I will hardly recommend you, please do attention in this lecture, because this type of lecture is very important for any competitive exam. Okay? At first, just recall what is the annihilating polynomial. Annihilating polynomial, I had seen in linear operator, if consider V be a finite dimensional vector space and consider T be a linear operator from V to itself be linear transformation, then a polynomial px in fx is said to be annihilating polynomial of px of t if pt equal to 0. As for example, consider fx equal to set of all polynomial with coefficient in the field f. Then annihilating polynomial means set of those polynomial in fx such that p with this operator would be 0. This I had seen in my previous video. I had seen all characteristic polynomial, minimal polynomial all belongs to annihilating polynomial. And there exists more annihilating polynomial without characteristic polynomial, minimal polynomial. Because annihilating polynomial means set of those polynomial which substituted with t, the value would be 0 operator. Okay? Now recall the characteristic polynomial and minimal polynomial. Let A be matrix from x to x will be n cross n matrix over an algebraically closed field K. Then we all of us know the characteristic polynomial of every n cross n matrix A is of the form t to the power n minus trace of A times t to the power n minus 1, and this would be continue plus minus 1 to the power n minus 1 times determinant of A. This is the characteristic polynomial of every n cross n matrix over algebraically closed field K. We all of us know this is. Just recall, I had seen in my earlier video, suppose V is a vector space and T be linear operator which maps from vector space to itself, and let lambda 1, lambda 2, lambda n denote the distinct eigenvalue of this linear operator with multiplicity d1, d2, dn. Then the characteristic polynomial is t minus lambda 1 to the power d1 times t minus lambda 2 to the power d2 up to t minus lambda n to the power dn. This is the characteristic polynomial of linear operator if lambda 1, lambda 2, lambda n denote the distinct eigenvalue with multiplicity d1, d2, dn. Okay? And minimal polynomial is, let V be a finite dimensional vector space of dimension n over the field F, and let T be linear operator on the vector space V. Then we know always the characteristic polynomial is the 0 operator which is denoted as characteristic of T. Here small t is the 0 operator on the vector space V. And let mt belongs to ft denote the monic polynomial of least positive degree which is satisfied by t. That means mt equal to 0 operator, because this is satisfied by the operator t. Then it can be proved by division algorithm for polynomials that if ft is a polynomial over the field f that's satisfied by t, then MT divides the FT over the field A. That means if FT be the characteristic polynomial, then MT always divide characteristic of the polynomial, which I had seen in my previous video. We all of us know this is. Moreover, by monic condition on MT, it follows that MT is always unique monic polynomial. This is very important. Always minimal polynomial is unique monic polynomial over the field A of least positive degree such that M substituted with T is 0 operator. Then the polynomial is denoted as MT, here the with small t. Minimal polynomial is denoted by this notation. Are you getting? OL. As for example, consider a matrix A belongs to M n cross n matrix over the field A. Then the minimal polynomial of the matrix A is the unique monic polynomial denoted by MAT over the field A of the least positive degree such that MA with A 0 operator means here the obviously 0 matrix. Are you getting? OL. Now I will see our first goal. Let lambda belongs to the member of field. Then characteristic of T with the value lambda equal to 0 if and only if empty lambda equal to 0 operator. In other words, that means characteristic polynomial and minimal polynomial have the same eigenvalue, means same zeros. Always this is true. The characteristic polynomial and minimal polynomial always have same eigenvalue. And the proof is such type, we all of us know minimal polynomial always divide the characteristic polynomial. Then characteristic of T equal to MTT times QT, where for some QT belongs to the field F. Therefore, MT lambda equal to 0. Then obviously chi t lambda equal to 0. Because suppose lambda is an eigenvalue of the linear operator T. Then there exists a non-zero vector V belongs to the vector space V such that by the definition of eigenvalue, since lambda is an eigenvalue of this operator, TV equal to lambda V. Then to prove lambda is an eigenvalue, MTT with the vector V equal to, just put the value TV equal to lambda V. Here put the value lambda times V, MTT times lambda times V, and since always V be a non-zero vector, that means that imply MT lambda equal to 0 operator. Are you getting? That means lambda is an eigenvalue of this minimal polynomial. Okay? OL. Now I will see some example which had come in Csir net exam with this topic. First example which had come Csir net June 2018. The question is, let V be a vector space over the field complex number with dimension n. And here the linear transformation means linear operator T from vector space to vector space will be linear transformation with only one as a eigenvalue. Then which of the following must be true? Option 1, T minus identity equal to 0 operator. Option 2, T minus identity to the power n minus 1 equal to 0 operator. Option 3, T minus identity to the power 2n equal to 0 operator. and option for t minus identity to the power n equal to 0 operator. For this, for shortcut, for at first I will see option 1 and option 2. For this, consider n equal to 2 and consider the matrix. Since here question has indicate in this linear transformation only one be the eigenvalue, so consider the matrix. Since here n equal to 2, so consider 2 cross 2 matrix 1 1 1 0. Since here I have considered the upper triangular matrix, all of us know for upper triangular matrix only eigenvalue be the diagonal elements. So obviously for this matrix only eigenvalue 1. So for this matrix t minus identity equal to 0 operator cannot possible. Are you getting? Oh, that means option 1 is a wrong option. And for option 2, if you consider same matrix, then notice since here I have considered n equal to 2, then n minus 1 means obviously 2 minus 1 equal to 1. Then t minus identity to the power n minus 1 means here 1. Similar to before, this is cannot be 0 operator. So option 2 also wrong option. At first I will say option 4. We all of us know characteristic polynomial is such type x minus lambda 1 times x minus lambda 2. This would be continue x minus lambda n. And since here has indicate only eigenvalue be 1. So this would be x minus 1 times x minus 1. This would be continue times x minus 1, which is equal to actually x minus 1 to the power n. Therefore, by Cayley-Hamilton theorem, we can tell every matrix satisfy their characteristic polynomial. Since here have considered linear operator, so by Cayley-Hamilton theorem we can tell every linear operator satisfy their characteristic polynomial. So by characteristic polynomial and Cayley-Hamilton theorem we can tell obviously fourth option is a right option. And since fourth option is a right option, so option 3 also right option, because here t minus I to the power 2n equal to 0 operator. Are you getting? Why I have told you characteristic polynomial Cayley-Hamilton theorem? This part is very important for any competitive exam. Oh yes. Now I will discuss one question which had come for 2019 exam. This question also basic question but very interesting. The question is here given A is 10 cross 10 matrix with the field real number. So the question indicate if A belongs to 10 cross 10 matrix with the field real number satisfies A square plus A plus I equal to 0 operator. Then we have to prove the matrix A in invertible. Notice here A square plus A plus identity equal to 0 operator means here given the annihilating polynomial. Okay, which is A square plus A plus I identity equal to 0 operator. This is the annihilating polynomial. By annihilating polynomial we have to prove is A is invertible. Just think at first. Here the idea is I will prove this by minimal polynomial and eigenvalue. Are you getting why I have considered it? I will prove this question by minimal polynomial and eigenvalue? Because we all of us know minimal polynomial divide the annihilating polynomial, and we all of us know the eigenvalue of minimal polynomial always similar to the eigenvalue of characteristic polynomial. So if we can to find all eigenvalue be non-zero, then obviously determinant of this matrix would be non-zero, or we can easily verify the matrix A is invertible. Are you getting? Oh well. Now we have to find the minimal polynomial. Here the annihilating polynomial a square plus a plus identity equal to 0. Notice this is actually this equation, x square plus x plus 1 equal to 0. The root of this equation would be b square minus 4ac, which is equal to 1 minus 4 times 1, which is equal to minus 3, which is less than 0. That means since b square minus 4ac less than 0, that means obviously all root of this equation be complex. Consider alpha beta be the root of this equation. Then the equation would be x minus alpha times x minus beta equal to 0. So since minimal polynomial divide the characteristic polynomial, so the possibility of minimal polynomial, case 1, it can be x minus alpha, possibility of minimal polynomial, or it can be x minus beta, or it can be x minus alpha times x minus beta. Now at first think, is x minus alpha be minimal polynomial? Just remind, minimal polynomial of roots of minimal polynomial always be eigenvalue of characteristic polynomial. From this equation we can tell alpha be the root of characteristic polynomial. But since alpha be the complex root, since here b square minus 4ac less than 0, so if alpha be the root, then obviously there exists there one root of their conjugate. But here from this equation we can tell here only one root. So x minus alpha be the minimal polynomial cannot be possible. Similarly, x minus beta cannot be minimal polynomial because beta be the complex root. So always there exists their conjugate root. So only possibility is x minus alpha times x minus beta. That means alpha beta be the root of minimal polynomial as well as characteristic polynomial. Okay? Oh yeah. Now, since here given A be the 10 cross 10 matrix over the field R. So, from this expression, I have understood there exists root alpha and beta, but their repetition, it can be alpha 5 times or beta 5 times. Their repetition here not be given. How many repetition possible? But notice, since alpha beta be non-zero number, so since alpha beta be not equal to 0, so determinant always would be non-zero. So obviously the matrix A is invertible. That means this option is true option. Getting? How minimal polynomial, characteristic polynomial, annihilating polynomial is very important. By annihilating polynomial and minimal polynomial, we can easily tell this matrix is invertible. Okay? So I will highly recommend you, please see today's video and my previous video with pay attention, because this topic is very important for any competitive exam. Okay? I will stop here. In my next video, I will discuss more example of any competitive exam. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos.